Good morning, sir. I'm heading towards the fourth and the final review of the semester and of our project. So, the main purpose of our project was to design a cost effective and efficient robotic cotton picker and effector to overcome key challenges in Indian cotton farming, such as labor shortages, cotton quality degradation, and the unsuitability of traditional harvesters for small and medium sized farms. So, the objectives were like it was very important for us to simply design a system and its architecture, the key components, and to implement and to prototype and refine the end effector using CAD modeling and 3D printing, which ensures operational readiness and compactness for field adaptability. So it was very important for us to simply design a system and its architecture in which we have developed end effector features which features a two finger mechanism, each embedded with rotating pins that mimic the twisting action which is required to pull the seed cotton from the ball, and the fingers are spaced to approach the ball from opposite sides, which allows for effective bilateral picking. And a single 12 DC volt motor which drives the both fingers using a bevel gear system which splits and synchronizes the motion. This significantly reduces component cost and power consumption as compared to the systems that use separate motors per finger. And these rotating pins in each finger are powered through a belt driven mechanism which allows continuous rotation during the picking process. So following are the some key components of the system, which includes two articulated fingers with rotating pins, a bevel gear arrangement for mirrored finger actuation, a timing belt system for rotating the embedded pins, and fourth one is a lightweight frame that is designed for robotic arm integration for assembly. So this setup ensures the synchronized motion, energy efficiency, and gentle cotton picking, which is suitable for small and medium scale farms. So by defining the key components of system, our next work was like mathematical modeling. In mathematical modeling, we designed and calculated the belt length, center distance, and the diameters of the pulley. While initial belt length estimation was essential for earlier design phases, the final system emphasizes bevel gear kinematics and torque distribution, which we have designed with the help of the formula like L equals to 2C plus pi. This is the diameter 1 and diameter 2's mean plus the circumference and all this. So this is the formula for the measuring length of the belt, center distance, and the pulley diameters. In the current system, the bevel gear is modeled to achieve equal and opposite angular displacement in both the fingers using a single input shaft. So we are using a single input shaft for the both fingers. The gear ratio we have kept is 1:1 for mirrored actuation and for ensuring symmetry in grasping action. Symmetry is the most important part in the mathematical modeling. Then CAD modeling and 3D printing. In previous reviews, we have seen that there were modifications done according to the requirement in order to fulfill the criteria to achieve particular functions, particular things. In first, second, and third review, we have seen a different we have seen different designs of the prototypes. uh, Figure 1 shows the first prototype with larger frame, which we can see here. Figure 2 shows the second prototype with smaller frame. Figure 3rd and figure 4th shows the full assembly. This is the full assembly, including the fingers. These two are the fingers, gear housing, pulley alignment, then frame, which was modeled using Autodesk Fusion 360, which helped simulate the motion path and test complement clearance. Here we can see all the components were fabricated using the PLA through the Fusion Deposition Modeling, that is FDM 3D printing. This assembly includes these fingers, then here the fingers in white or grayish color, then gear housing in yellow color, and pulley alignment with the frame in black color. Here we can see, and the belt system is aligned here with the pulley. These pulleys are connected to each other through the gear mechanism as well as the belt mechanism. So this system is whole connected. Here we can see the angular displacement while the gear moves or rotates here in this assembly. The belt tension also increases, and the rotating action is taking place, and that's how the cotton is picked into this area of white area. Then that slides towards the end of the finger and gets vacuumed in the machine. So all the components were fabricated using PLA through FDM 3D printing, offering fast turnaround and sufficient rigidity for initial testing. This prototype assembly was manually inspected and tuned for alignment and gear meshing. So if we talk about results and discussion, the development of this end effector is progressed through the 3 major design iterations. Like prototype 1, which featured a large and bulky frame with an open belt mechanism where each finger was powered independently. This setup led to issues such as poor belt tensioning, misalignment, and unsynchronized finger motion, ultimately affecting the portability and reliability of the system. Then we went for a second prototype with a smaller frame, which was designed for compactness, for improving mounting precision and finger stability while retaining the belt mechanism. However, the need for the separate actuation for each finger still posed operational complexity. To address this issue, we went for third iteration. So prototype 3 or prototype 3rd was introduced to overcome all the challenges and constraints we were facing, in which we introduced a bevel gear. So here we can see that in first prototype there is no bevel gear, in second prototype there is no bevel gear, but in third and final prototype we can see a bevel gear mechanism that enabled both finger to to operate synchronously, okay, using a single 12 DC motor. So here this bevel gear mechanism is connected to the 12 volt DC motor through the pulleys and mountings. So the belt system was preserved, this black in color. This belt system was preserved for rotating the embedded pins, while the bevel gears provided mirrored finger motion. This is a synchronized motion. It's a symmetrical level of motion, or the motion at the same time of the both fingers. This final iteration achieved mechanical simplicity, which reduced component count and compact form factor, which renders it more suitable for robotic integration. In real world cotton harvesting scenarios, we can use this final prototype, the final iteration. So this is the final prototype, the cotton picker end effector. You can fully see this. This is our project. Next we went to the mechanical performance. Once the final prototype exhibited smooth synchronized finger motion via bevel gear actuation and stable pin rotation through precise belt alignment. Then the design showed improved compactness, reduced friction, and eliminated common failures like slippage and jamming, enhancing its suitability for Indian field conditions. So now we are heading towards the operational readiness. Manual tests were confirmed, and reliable gear engagement and consistent finger motion over repeated cycle. So the manual tests were taken, in which it confirmed the reliable gear engagement and consistent finger motion. And then the single motor bevel gear configuration proved efficient and compatible with mobile platforms, making the system ready for controlled lab testing. While producing the results, the setup led to issues, so many issues such as poor belt tensioning, misalignment, unsymmetrical finger motion, ultimately affecting portability and reliability. But the system is currently manual, lacks sensing capabilities, and has not been field tested. So the components are made from PLA, which may not endure real world agricultural stress. This is a constraint. This is the first constraint. And energy performance and long term durability remain unvalidated. The future work we can do is like the future improvements will be including integrating a robotic arm and vision system, using durable materials like ABS or nylon, and conducting full scale field trials to assess real world performance and scalability. So in conclusion, I would like to conclude the design and development of low cost dual finger cotton picking end effector, optimized for small and medium scale sized farms, through 3 iterative prototypes. The system evolved into a compact, mechanically efficient solution using a single 12-hole DC motor and a bevel gear mechanism for synchronized finger actuation. In the final prototype, we demonstrated the reliable performance in manual testing with improved alignment, reduced complexity, and stable rotation of embedded pins, while the current system lacks automation and field validation. It lays a strong foundation for future integration with robotic arms and vision based perception. The proposed design holds the promise as a scalable, affordable alternative to conventional cotton harvesting methods, particularly in labor constrained agricultural setting. So the limitation, like this system is currently manual, which lacks sensing capabilities and has not field tested, and the components are made from PLA, uh, which may not endure real world agricultural stress. So to overcome this problem, we can use durable materials like ABS or nylon, and conducting full scale field trials to assess the real world performance and scalability. So that's it. Thank you so much.